In this video, we're going to discuss a couple theorems that apply to derivatives. One of them will extend on to integrals later on, but we're going to just kind of take a look at it here. The first one is Rolle's theorem. And in this, it says if f is continuous on a closed interval and differentiable on that same open interval. Okay, and so we're looking at some closed interval of the function. It does not have to be the whole function. Okay, continuous on that closed interval and differentiable on the open interval. If there are two y values of that function that are the same, meaning that function comes up, like starts at one number, goes down, and then comes back up to the number and the y values, or starts at some y value, goes up and comes back down to the y value, then, okay, so we have basically a horizontal line connecting 2 points on the graph, then there's at least one number, c, that is in that open interval, such that the derivative is 0. In other words, if f is continuous on some closed interval and differentiable on the open interval, this guarantees that if you can find two y values, then you have a relative max or min. Okay. All right, so let's take a look at this. It says part A in this particular function. This is using Rolle's theorem. Part A says find the intercepts of the function and show that the derivative equals 0 at some point between the two intercepts. Okay, so find the intercepts. Step 1. To find the intercepts, we have to set y is equal to 0. That's where the intercepts are when y is 0. So we call that y is equal to 0. 0 is equal to x times the square root of x plus 4. This implies that x equals 0, or the square root of x plus 4 equals 0, which in turn says that x equals 0 or x equals -4. Okay, so if you solve the square root of x plus 4 is equal to 0, then you get x equals -4. All right, so there's our two endpoints. And so we're considering then the open interval 0, I'm sorry, -4, -4 to 0. That's one of them. The other one that we're considering is also that closed interval, because it is defined at the endpoints. If x is in fact -4, then you get 0, and if x is 0, you get 0. And so, and we're looking at -4 to 0 inclusive. Those are our two values, or our two intervals. It is continuous on that closed interval. There are no values that we can't put in for x that it won't come up with a good value for y. And the question now is it differentiable on that open interval? Well, as it sits right here, I don't see any problem with it. We have x to the 3/2 as far as the dominant force. And so initially, it doesn't look like it has a cusp. It doesn't look like it has a step break, that sort of thing. But we don't know whether the derivative goes off to infinity in any of that, in that interval. And so let's check that out. Right now, here's what we're looking at. If we were to quickly sketch a graph of this function, we know that we have a point here at -4 and a point here at 0. And now if we just choose a number in there somewhere like -1, -1 plus 4 is a +3, the square root is going to be positive. -1 times some positive is going to be a negative. And so we're going to be hovering down here. That's where we're going to be hovering. So we're really searching for this point here to see if that point exists. So let's find its derivative. I'm going to use the product rule. You can multiply this through if you so choose, and use x to the 3/2 plus and work it that way if you want. That's entirely up to you. I'll use the product rule in this case. So I take the derivative of the first, which is 1, times the second, plus the derivative of the second. Now the derivative of the square root of x plus 4 is 1/2 the square, and this is the x plus 4 raised to the -1/2, which is 1 over 2 roots of x plus 4 times the first x. And so this is actually, let's see here, we have x over 2 root x plus 4 plus root of x plus 4. Okay, so now the question is, do we have any problems in here? If you notice, we don't have any problems until we hit x equals negative 4. X equals negative 4, we have an issue down at the bottom because this makes that equal to 0. Okay, luckily though, it says, is it differentiable on the open interval? So the open interval is not including that endpoint, so we're safe. Okay, so this is differentiable everywhere in that interval, that open interval from negative 4 to 0. So that's good. Okay, so now, and show that it has to be. Okay, well, we kind of did. Now we have it, it's differentiable everywhere, so we have to show that somehow that derivative can be 0. And so we want to say, okay, well, where is the derivative 0? So where does 0 equal x over 2 root x plus 4 plus root x plus 4? Okay. To do this, let's go ahead and let's get a common denominator so that we can get everything all over 1. And so I'm going to multiply this part right here, top and bottom, by 2 root x over plus 4. So if we do that, then we end up with x times 2 root x plus 4 times root x plus 4 all over, plus, that's x plus, by the way, all over 2 root x plus 4. Okay, so now we have 2 times that squared is 2x plus 8. So we have x plus 2x plus 8 all over 2 root x plus 4. That's 0. Now we have 3x plus 8 over 2 root x plus 4. So that whole thing is 0 when 0 is equal to 3x plus 8, or if you solve this for x, you get a negative 8/3. So here's the value, and we had to show that f of x is equal to 0 at some point in between the two intercepts. Negative 8/3. Now, negative 8/3 is slightly less than there's slightly greater, pardon me, than negative 3, and that is in fact in our interval. And so we're good. And that's how you figure these out. Okay, so here's Rolle's theorem and an application of it.